Alright, hi there guys, my name is Wilfrid and I'm a senior math tutor, and today I'll be covering 10 questions related to functions, algebra, and calculus. So a little bit backstory upon myself. I graduated from McMaster with a major in biochemistry and a minor in mathematics. And if you have any other issues with math or chemistry or calculus, please submit them to OneClass, your questions, and we'll get to them as soon as possible. So other than that, let's just jump right into it. Okay, so the first question reads, what is the solution to the system of linear equations? And they give us two linear equations here. 2x plus y equals 1, and 3x minus y equals negative 6. So another way that we can rephrase this question about finding solutions to a system of linear equations is to find the point of intersection between these two line equations, okay? So that's an alternative way of writing this question. And so one of the solutions and one of the ways that we can solve this system of linear equations is by graphing these two lines and identifying visually where they intersect. So there are two other methods that we can use to solve the system of linear equations, and the junior tutor outlines them here. There's a substitution solution and there's an elimination solution. So I'll run through both of them today. Okay, so for the substitution solution, we basically want to sub one of the linear equations into another. And how we're going to do that is we're going to, for one of the linear equations, we're going to isolate for the variable y or x. Really depends on how you feel, but we're going to isolate for the variable y. Okay, so let's first do substitution here. Substitution. Okay. So the first thing that we want to do is we want to define which equation is which. Okay, so if we write out our equations, 2x plus y equals 1, and 3x minus y equals negative 6. I'm going to label this equation 1 and equation 2, so there's no confusion here, okay? So for equation 1, we're going to transform it by isolating for y. So we're going to move this 2x to the right-hand side. To do that, we're going to subtract both sides by negative 2x, and we get this. So y equals 1 minus 2x, and we're going to call this equation 3, okay? So now, we're going to sub equation 3 into equation 2. Okay? And what I mean by sub is that we're going to take y, which equals 1 minus 2x, and sub it into 3x minus y equals negative 6. And particularly, I'm going to sub in y into this y here. Right? So now we have 3x minus 1 minus 2x equals negative 6. And if I were to simplify and isolate for x, this is what we will get. We'll get 5x equals negative 5. Okay? And now that we have isolated for x, we can just divide both sides by 5 and we get x equals negative 1. So now we have found the x value for the solution for our system of linear equations. Now all we need to do is sub this back into 3, for example, and we'll get our y value. So we sub it back into 3, we get 1 minus 2 times negative 1, and we get 1 minus 3. Okay? So therefore, the solution is negative 1 and 3. Okay? So that is the first technique that we are using, substitution. And basically, this is the computational method of finding the point of intersection between these two line equations. Okay, so now let's talk about elimination. Okay. All right. So elimination is kind of different in the way that we are going to basically subtract these two linear equations from each other. And what I mean by that is that we're going to, first of all, we're going to write them out like this. And we're going to treat this like a subtraction or addition, depending on what we want, okay? But the main thing that we want to do is we want to eliminate one of these variables in both of these linear equations, okay? So you see here that if we were to add these two linear equations together, so we add the left-hand side together and the right-hand side together, we would get rid of our y variable. So if we were to add both sides, we would get 5x plus minus, so y, positive y minus y is 0, and then we would have negative 6 plus 1, which is negative 5. Okay? So we see here where the term elimination comes in, right? So for elimination, we want to get rid of one of the variables, okay? So by getting rid of one of the variables, we can isolate for the other one and solve for it, okay? And in this example, it's very easy for us to eliminate the variable, but sometimes you have to multiply one of your linear equations by a constant to be able to eliminate that variable. For example, if, let me write out an example real quick. If we had, instead of 2x plus y, we had 2x plus 2y equals 1, and we had 3x minus y equals negative 6. If we were to add these two linear equations together, we wouldn't be able to eliminate one of the variables. So therefore, we would have to multiply this by 2 first, okay? So we have to multiply this by 2, we would get 2x plus 2y equal 1 for our first linear equation. And we multiply both the left-hand side and the right-hand side by 2, we get 6x minus 2y minus 12. And here, in this example, we can now add these two linear equations together. Sometimes you have to subtract, sometimes you have to add, sometimes you have to multiply it by a constant, sometimes you have to divide by a constant. And really, the technique that you use really is dictated by how you want to eliminate that variable, okay? In another case, if I wanted to eliminate the x variable, then I would have to multiply this first one by 3 and the second one by 2 to get both sides to be 6x, right? But here I recognized that the y variable is easily eliminated, so that's what the one that I want to eliminate, okay? So whenever using the elimination technique, always recognize and identify which variable is easier to eliminate. Is it the x variable or the y variable? And by doing that, you save yourself a huge headache of trying to multiply or divide by constants, okay? So going back to our question here, we have now eliminated the y variable, so now we have 5x equals negative 5, right? So now if we isolate for x, we get x equals negative 1, okay? So now we found our x value of our solution, and now we just have to plug it back into one of our linear equations. So let's do this, and plug 1 into 2x plus y equals 1, and we get negative 2, sorry, we write 2 times negative 1 plus y equals 1. If we isolate for y, we get y equals 3. And therefore, solution is negative 1 and 3. Okay, so the last thing that I want to point out after all of this is that there are 3 possible solutions to a system of linear equations. So the first possible solution is that there's one point of intersection, right? If we were to think about it in the beginning when I said that an alternative way of explaining this question is to say that find the points of intersection between these two lines, right? So the first option is what we solved here. There's one point of intersection, right? The second type of solution is that there is no point of intersection. And this is where the lines are parallel to each other and that they never touch each other at all. Okay? What I mean by parallel to each other is that, that they both have the same sign of a slope, so they either both have a positive slope or a negative slope. And also their slopes are also the same, but the y-intercept is different. Okay? And finally, the third type of answer is that there's infinite point of intersection, and this is where both lines in the system are the same. So they're essentially the same lines, so they intersect infinitely. Okay, and I guess another point that I'll leave off with is that the system of linear equations does not need to be just 2. It could be 3, it could be 4, it could be 5. And when you increase the numbers, then you're trying to find a point of intersection between all those lines. Okay. So that's the last thing I'm going to leave off on. And other than that, this solution is correct. Sorry, give me a second. My audio is not working still. Hello? Can you guys hear me now? Hello? 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 Okay. Can you guys hear me now? I believe you guys can. Okay, so I think my mic was functioning for the whole question. So I'll quickly run through the question again. So the question reads, what is the solution to the system of linear equations? And the linear equations here are 2x plus y equals 1 and 3x minus y equals negative 6. Okay, so how I found the solution to the system of linear equations is by what the junior tutor suggested to us. So there's two different techniques. One is substitution and one is elimination. So for the substitution technique, you basically want to isolate for one of the variables within your linear equations and sub it into the other linear equation. So here, I first of all, we need to label the linear equations within our system to be clear on which one we're isolating for. So you can choose either linear equation to isolate for, but I chose equation number 1. I isolated for variable y. So once I isolated for variable y, I took this this new equation, which is number 3, and subbed it into our equation 2. So I took the y and I plugged it into negative y here, and I isolated for x. And by isolating for x, I found the x value of our solution, which is negative 1. So after that, I plugged negative 1 back into one of the linear equations to find the value of y. And by doing so, I found the value of y to be equal to 3, and therefore the solution to this linear equation is negative 1 and 3. And I previously mentioned before that alternative way of listing or writing this question is to find a point of intersection between these two lines. Okay? So now that we're talking about elimination, this technique is a little bit different, and where you're trying to get rid of one of the variables by adding or subtracting the linear equations together. In this case, in our example here, I added both of our linear equations together. So what I mean by adding is I'm not trying to add them like in the conventional manner. I'm basically adding together the left-hand side and adding together the right-hand side. And by doing so, I was able to get rid of the y variable and isolate for the x. So I found the x value of our solution, and then I plugged it back into one of our linear equations to find the y value of our solution. And then here I described that in our actual example, or our specific example, I only had to add together the linear equations. However, this is not always the case, because sometimes you're given two linear equations which the variables are not so easily eliminated. So that means that you'll have to use different techniques like multiplying or dividing your linear equations by a constant, or subtracting your two linear equations together, or a combination of all those factors here. And I use this example to show it, right? So if our linear equations were 2x plus 2y equals 1 and 3x minus y equals negative 6, I would have to multiply our second equation by 2 to be able to eliminate the y variable. And the final note that I touched on is that you can choose either x or y to eliminate, but I would say that a tip is that you want to identify which variable is easier to eliminate. Is it the y variable or the x variable? In our specific example, it was the y variable that was easy to eliminate, so I did that instead. Okay, so basically after that, the solution is correct and we can move on, so good job. Cool. All right, I hope that you guys can still hear me. I believe that you guys can, but hopefully you guys can. Okay, so let's talk about question number 2. So question number 2 asks us to find the point on the line y equals 3x plus 4 that is closest to the origin. Alright, so I need to define what our origin is first, and if you guys don't know, so, whoops, it's blue for some reason. So on our Cartesian plane here, and we're going to label the axes, the origin is basically the center of our Cartesian plane, or the coordinate 0, 0. Okay, so they're asking us, given our line, so this is not actually the line, but I'm just doing for illustration, given our line, which is y equals mx plus b, find the point on the line here that is closest to our origin, right? So along this whole line, which point on our line is closest to the origin? Okay, so that's what they're asking us to do. So, you guys can obviously graph this line and visually try to locate it, but there's a computational method of doing this, okay? And it requires us to know what the distance formula is, okay? So the distance formula is d equals the square root of x2 minus x1, squared plus y2 minus y1 squared, okay? Where x1, y1 is 1 point, and x2, y2 belong to R2, okay? So basically the distance formula helps us to calculate the distance in units between two different points, okay? So we're going to use this formula to calculate the closest point on our line to the origin, okay? So let's say that let point xy be a point on y equals 3x plus 4. Okay, so if xy is a point on y equals 3x plus 4, the distance from that point to the origin is as such. X minus 0 squared, right? Because x1 is going to be 0 and y1 is going to be 0. So, and x2 is going to be x and y2 is going to be y minus 0 squared. Okay, so this is the distance in units between our point xy on our line, y equals 3x plus 4, from that point to the origin. That's the distance formula, right? So if we were to simplify this, we would get d equals the square root of x squared plus y squared. Okay. So the second thing that I want to do is I want to plug in y, right? So we know that y equals 3x plus 4, so I'm going to plug that in. So if we plug in y, we get x squared plus 3x plus 4 squared. Okay? And if I were to simplify this, it would be the square root of x squared equals, let me just write out the entire thing. So I'm going to expand this bracket. So it'll be 10x squared plus 24x, oops, plus 24x plus 16. Okay? So I expanded this bracket and then I added everything together. And now we have found a distance formula from this point on our line to the origin. However, that's not the only way to describe what we see here, okay? We have created a new function that calculates the distance of any point on the line to the origin, okay? So now that we have found a function like this, we're going to optimize this function by finding its derivative and finding when the derivative is equal to 0. And when we find that optimized point, we have found basically the point which is closest to the line, or to the origin, okay? And I'll explain a little bit into detail why, all right? So the first thing that I'm going to do, now that I have found our function, is I'm going to get rid of the square root. So I'm going to square both sides, okay? And the reason why I do this is so that our derivative is a lot simpler to calculate and we don't need to worry about it because the minimum of d and d squared is going to be the same, okay? So now that I'm going to find the derivative, I'm going to prime this and we're going to find the derivative of this. So it's going to be 20x plus 24, okay? All right, so let me recap what I just did. So first of all, I've defined a function which measures the distance from any point on our line, y equals 3x plus 4, to the origin. And then I reasoned that if I were to find the critical point of its derivative, I'll be able to find the point on the line that's closest to the origin. Okay? So then, now I did the derivative, and I made it easier to calculate the derivative by squaring both sides, because I reasoned that the minimum, or the critical point of d squared and d are going to be the same. Okay, and it's going to be the same. Right, so now that I found the derivative, this is what it is, and we're going to set d squared prime x to be equal to 0. And to do that, we're going to calculate the value of x, which will make this equal to 0. So then, if 20x plus 24 is equal to 0, then we get 20x minus 24. We get x equals negative 12 over 10, and negative 6 over 5. Okay? So, why did I try to find the critical points of our of our derivative, okay? So when we set the derivative to be equal to 0, we're locating the point of our original function where there is a horizontal tangent. And there's a theorem in calculus that states that the horizontal tangents on a function relates to either a maximum, a minimum, or a saddle point, okay? In this case here, we only have one value of the function, which is makes the derivative equal to 0. And this is the only critical point, okay? So we're going to look at this critical point and identify whether or not this is a max or a minimum, okay? And most likely it's going to be a minimum because of the nature of how our derivative works, or how our original function works, okay? So now that we have found the value of, or the critical point of interest here, which makes our derivative equal to 0, we're going to plug it back into our original function, okay? So our original function is our line function here, because we have now identified the value of x, which is closest to the origin. Okay, so now we just need the y-coordinate, right? So we're going to plug x equals -6/5 back into y equals 3x plus 4. Okay, so we have found the minimum point, which is -6/5, and now we're going to plug it back into our line equation. So y equals 3 times -6/5 plus 4, and this would be -18/5 plus 4, which equals like 2/5. Okay, so therefore, -6/5, 2/5 is the closest point to the origin. Okay. So by optimizing this function, we have found the value of x, which is the coordinate for the point on the line that's closest to the origin, okay? So in other words, when we are calculating for the derivative of this function, right? So this function measures the distance of every point on the line to the origin, okay? So we're trying to find the critical point of this. We're trying to find the point on the line which makes the derivative equal to 0, which means that that makes the distance equal to its minimum, okay? So when the derivative is equal to 0, the x and y coordinate of that function, I guess, relates to how the distance is minimum in our original function here. So that's the rationale behind finding the derivative equal to 0, okay? And once I found the x coordinate, I just plugged it back into our line equation, and we found the y coordinate. And by doing so, we have identified the closest point to the origin. So the solution is correct. Okay. Alright, so which number line represents a solution set for the inequality 2x minus 6 is greater or equal to 6 times x minus 2 plus 8? Okay, so we have to find the values of x which will satisfy this inequality, right? So there's one way that we can do this is we can use guesswork, right? We can just guess values of x, and hopefully it would make the left-hand side always greater than or equal to the right-hand side. But there's a much more logical way of going through this. So the first thing that we notice here is that there's the values of x, so there's a variable on both sides, which makes it very hard for us to guess or to evaluate what values of x will satisfy this inequality. So we're going to manipulate our inequality to basically isolate for a value of x, okay? So let me write down our inequality again. 2x minus 6 is greater than 6 times x minus 2 plus 8. So the first thing that I'm going to do is I'm going to expand this right-hand side. So 2x minus 6 is greater than or equal to 6x minus 12 plus 8. Okay. Now I'm going to move our values of x, or our variables of x, to the left-hand side and our constants onto the right-hand side. So to do that, I'm going to subtract both sides by -6x. So we have 2x minus 6 minus 6x is greater than negative 12 plus 8. And I'm going to add both sides by 6 to get this negative 6 to the right-hand side. So we get 2x minus 6x greater than or equal to negative 12 plus 8 plus 6. Okay, now that we're here in this step, we're just going to simplify both sides. So we have negative 4x is greater than or equal to 2. Okay? So now we're at this step. We want to get rid of negative 4, right? So we're going to divide both sides by negative 4. And there's a rule with inequalities when you're isolating for them, is that whenever you're dividing or multiplying by a negative number, you have to flip your inequality sign. Okay, so we're going to flip our inequality sign because we're dividing by negative 4, and it's going to be 2 divided by negative 4, or x is less than or equal to negative half. Okay, so this inequality that we have here is the same thing as this inequality. We just basically simplified everything and organized it in a way that is easier to interpret. So now, we now know what the values of x that will make this inequality true. So any value of x that is less than or equal to negative half is going to make this inequality true. So now, we're going to set up our number line here. So if we have our number line, right, where this is infinity, and this is negative infinity, and this is 0, our solution to the number line is going to be, so if this is negative half here, it's going to be from here and beyond, right? So x belongs to this part of our number line. Okay? So that's what it means by find the number line which represents a solution set for the inequality. You have to draw the number line, and you have to identify which part of the number line satisfies your inequality. Okay, so the solution is correct. Nice job. Okay. Question number 4. So question number 4 reads, if the function f of x is equal to 5x minus 12, what is the inverse of f of x? Okay, so like I described previously, so the function f of x basically connects the domain of a function to its range. So okay. So the inverse function basically connects the range of the original function back to its domain. So kind of like it's like a reverse like mechanic, right? So it basically returns the range back to its domain, right? So in this case, the domain of the inverse function is the range of the original function, and the domain of the original function is now the range of the inverse function. So that's how the inverse works, okay? And the main method of finding the inverse of a function is as such. Basically, what we're going to do is that we're going to first state our original function, and we're going to swap our variable x, or our independent variable, for our dependent variable. So first we're going to do this. X equals 5 f of x minus 12. So once we swap it, now we're going to isolate and solve for f of x again. So to do that, we're going to move 12 to the other side, so x plus 12, and we're going to also divide both sides by f of x, or by 5, and this is what we get. F of x equals x plus 12 divided by 5. And this is how you simply find the inverse function. And finally, we're just going to write f of inverse, because that's the correct notation, equals x plus 12 divided by 5. Okay, so that's how you find the inverse function. You basically swap your independent and dependent variable, whatever they are, and then you want to solve for the dependent variable again, and by doing so, you're able to find your inverse function. Okay, so this solution is correct. Good work. Okay. So, question number 5. How do you solve for x squared minus 5x plus 3 equals 0 using the quadratic formula? So usually, you can solve for the zeros, solutions, or roots of a quadratic function by finding its factors. And by finding the factors, you can easily identify what the zeros, roots, or solutions are. The quadratic formula is a special formula that is used in cases where your quadratic function is not easily factorable. Okay, this includes when your function does not have a perfect square, or there's no combination of factors which will easily identify your zeros. Okay, so the quadratic formula finds your values of x, or your solutions or roots, that solve this quadratic equation by doing this. So it's negative b plus or minus b squared minus 4ac divided by 2a. Okay, where a, b, and c are from the coefficients of a squared, ax squared plus bx plus c, which are your coefficients of your quadratic equation or quadratic function. Okay, so basically by plugging in your coefficients here and solving for both the positive and the negative, you're able to find the zeros that will solve this quadratic function. All right, so let's do it for this one. So first of all, we have to identify that this is not easily factorable. You guys can pause this video and you guys can try, but it's not easily factorable. So we're going to use the quadratic formula here. So first we're going to write it down again. And we're going to use x equals negative 5, or sorry, positive 5, plus or minus 5 squared, or negative 5 squared minus 4 times 1 times 3 divided by 2 times 1. Okay. Alright, so if we were to simplify our square root in there, we have 25 minus 12 divided by 2, and then we have 5 plus or minus root of 13 divided by 2. Okay, so now we have two different options here. We have x equals 5 plus root 13 divided by 2, or we have the negative, which is x equals 5 minus root 13 divided by 2. Okay, so if we were to plug this 0 and this 0 into our quadratic function here, it'll make the left-hand side equal to the right-hand side, or it'll make our quadratic function equal to 0, right? And we're not able to find these two zeros or solutions by just factoring, right? This is solely because of the quadratic formula. So the solution is correct. Good stuff. All right. So the next question asks us to find the dimensions of the rectangle of the largest area that can be inscribed in a circle of radius r. Okay, so what does it mean for a rectangle to be inscribed within a circle of radius r? Okay, so imagine that we had a circle with radius r here, okay? So it means that the rectangle is inscribed if the rectangle is within the circle, okay? That's what it means by inscribed, right? So obviously you can find the rectangle of largest area and the dimensions of that rectangle by having the rectangle touch the vertices of the rectangle touch the circle. And by doing so, you can ensure that you will find the rectangle of the largest area, and you can find those dimensions. Okay? So basically, we're going to try to find the dimensions. So we're going to try to, first of all, find a function that defines the area of the rectangle in terms of the radius of the circle, and in terms of the values of x or y. Okay? So looking at our diagram here, it is very clear that first of all, that the rectangle has to be touching the circle. Okay, so that means that the radius is also the diagonal, is half the diagonal of the rectangle. Okay, and the diameter is the full diagonal of the rectangle. Okay, so that means our height of the rectangle is going to be this. Okay, so first of all, we're going to try to use Pythagorean's theorem here. So Pythagorean theorem states that r squared is equal to x squared plus y squared. Okay. So the hypotenuse of a right angle triangle is equal to the squares, the sum of the squares of their sides, right? So we're going to isolate for y here. So y is equal to r squared minus x squared. Okay. So looking at our diagram here, this is the length of y, right? And we see here that our rectangle, the height of the rectangle is going to be 2 times y, right? So there's 2 lengths of y here for our height of our rectangle. So the height, I guess the length, I don't know why I'm saying height. The length of a rectangle is going to be 2y, or 2 times r squared minus x squared. Okay, what about our width? So the width is going to be 2x. Okay? So therefore, our area of the circle, right, what's the formula for area of a rectangle, sorry, is going to be width times length, right? But that's also equal to 2 times r squared minus x squared times 2x. Okay? And if we're to simplify this, it would be 4x times the square root of r squared minus x squared. So now we have found a function that defines our area of the rectangle in terms of the radius of the circle, and also the dimension of the x value. Okay? And another thing is that this x value defines the length and the width of our rectangle. Okay? So now that we have found our function that varies the area of the rectangle based on the radius of the circle and also the x value, we can now optimize, like in our previous question, for the maximal area of this function. Okay, so we're going to try to find the maximum of this function. And to do that, we're going to again find the derivative of our function here and try to find the critical points. And if we find the critical points of this function, then we can find the maximum. Okay? And if we find the maximum, then we can find the dimensions of our length and our width. Okay? So that's the rationale behind all this thinking here. Okay? So, another thing to note is that the radius of our circle is going to be kept constant, and we're not going to be deriving in terms of r. Okay? Because that's not what the question is asking. The question is asking for us to look for the length and the width, and we know the length and the width is dependent on this value x. Okay? So, we're going to derive our function in terms of x. Okay, so we're going to use a chain rule here. So that means that we're going to derive this first function first, or not the chain rule, we're going to use the product rule, sorry. So we're going to use the product rule, we're deriving this first function first, so it's going to be 4 times the root of r squared minus x squared, and we're going to add it to the derivative of the second function, which is going to be half of r squared minus x squared to the power of negative half. Oops, that's not a 1. Times the derivative of the inside function, which is going to be negative 2x. Okay? Did I forget anything? Oh, and times 4x. Okay? So if I were to simplify this, we would get 4 times r squared minus x squared minus 8x squared divided by, or minus 4x squared divided by the root of r squared minus x squared. And if we were to simplify this further, we would find that this would equal to 4r squared minus 8x squared divided by the root of r squared minus x squared. Okay, so you guys can pause the video and you guys can simplify this, but basically I moved everything under the same denominator by multiplying this first term by square root of r squared minus x squared, and then I simplified to find this derivative function. Okay, so now we're going to set this derivative to equal to 0, because we know that a critical point relates to either a maximum of our function, a minimum of our function, or a saddle point. Okay, so if we set this equation to equal to 0, we notice here that this is a rational function, right? So to set this equation to equal to 0, all we have to do is to find the value of x which will make the numerator equal to 0. And that's what we're going to do. So 0 equals 4r squared minus 8x squared. And if we isolate for x, we get 8x squared equals 4r squared. We have x equals the square root of r squared divided by 2. Okay, maybe I should explain this further. We have x squared equals 4 divided by 8r squared, and we have half r squared. And then we have root both sides, and we have r divided by 2. Root of r divided by 2. Okay, so this is the value of x, which will basically maximize or minimize our function here. Okay. Now, we want to understand here that this critical point here is going to maximize our function here, and that's because of the nature of our function. Okay. This is a square root function multiplied by a variable of x, and we know that there's only maximum of this function, and the minimum of this function does not exist. Okay, so with that in mind, we can now consider this value of x to be maximizing our area of a rectangle, and by doing so, we can now find the dimensions of such a rectangle. Okay, so if x is equal to the square root of r divided by 2, then the width, which is equal to 2x, is going to equal 2 times the root of r divided by 2. Okay, and the length is going to equal 2 times the square root of r squared minus, what's length equal to again? Minus the r minus the r times the root of 2 divided by 2 squared. Okay, so if we were to simplify for this, we'll get 2 times r squared minus 2r squared divided by 4, and we would get 2r squared minus r squared divided by 2, and we would get 2r squared divided by 2. Okay. And if we keep going with this, we would get 2r times root of 2 divided by 2, and we would get r times root 2. Okay, so these are the dimensions that will maximize the area of our function according to the function that we have derived based on using the Pythagorean theorem and also using our area formula, right? So by optimizing this function, and by finding the critical point of this function, we're able to identify the dimensions and where the largest area rectangle exists within the circle. Okay, and the dimensions of that is width is 2 times root of r divided by 2, and our length is r times root 2. Okay. Wait, sorry. This is, I think my x is wrong actually. Now I'm looking at it. X should be sorry. So this is actually wrong. This should be 3 times r root 2 divided by 2. This equals r times root 2. Okay? Alright, so the solution is correct and we can move on. Alright. So the next question asks us to graph and describe the end behavior of this polynomial function rx equals negative x to the power of 5 plus 5x cubed minus 4x. Okay, so I'm just going to write this down here. Okay. So the first thing that we want to do is that to graph it, we need to identify the zeros of our polynomial function, right? So we want to identify the values of x, which will make our graph intercept the x-axis. Okay. So to do that, first of all, we're going to factor out x here, or negative x, and we get x to the power 4 minus 5x squared plus 4. Okay. So we're going to factor this, right? So it'll be x squared minus 4 times x squared minus 1. Okay, you guys can pause the video and you guys can see that these are the factors of this term here. And we recognize here that these are the difference of squares, right? So we can further factor this to be negative x times x plus 2 times x minus 2 and x times x minus 1 times x plus 1. Okay? So we found our zeros, and our zeros are x equals 0, negative 2, 2, 1, and negative 1. Okay? So now we have found our zeros, we can plug them in here. Okay? This is x, and this is y. And we have zeros at 0, negative 1, 1, 2, and negative 2. Okay? Let me draw this better. Alright, so the next thing that we need to know is the end behaviors of our function, right? Because this is going to dictate which way the function faces. Okay, so there's two different options that the function looks like is coming from the positive side to the negative side, or from the negative side to the positive side. So these are the two different behaviors of the function, and they're dictated by the end behaviors, right? So what I mean by end behavior is, how does the function behave when it's approaching infinity and negative infinity? Is the function tending towards infinity, or is the function tending towards negative infinity? Okay, so to do that, to simply do that, all you really need to do is plug in a huge number into your original function. In this case, I'm just going to plug in an infinity, the concept infinity, into our function, and to see whether or not our function is approaching infinity or negative infinity. Okay, and when you're plugging in infinity, all you really need to do is examine the leading term, because the leading term is what's going to define the behavior of your function. Okay, so if I were to plug in infinity into our function here, right? So let's say, r of infinity. Okay, you guys can plug in a huge number if you want to actually compute what the value is going to be, but I'm just going to say infinity for now. So if I plugged in infinity into our leading term here, we get infinity to the power of 5, which is infinity, with a negative number here, right? So this is equal to negative infinity. Okay, and if you guys want to plug in a huge number, let's say, let's plug in r of 1,000. Okay, so that's not really a big number, but it's something that we can work with. And 1,000 to the power of 5 with a negative is going to be a negative 1,000 to the power of 5, right? So we have found that our end behavior as the function tends towards infinity is coming from the negative side, right? So that means that as our function tends towards infinity, it's going towards negative infinity. Okay? How about the other way around? What if we plugged in negative infinity, or negative 1,000? Okay? If we plugged in negative infinity here, we would get that we would have negative times negative infinity to the power of 5, right? And we know that when a negative number is powered to an odd exponent, it retains its negative sign. So now we have negative to the negative infinity. We have positive infinity. So we have identified that our end behavior for our function, as the function tends towards negative infinity, is that it's heading towards positive infinity. So it's going this way. Okay. So now that we have our end behaviors in sight, we can now draw our polynomial. Okay. So our polynomial, basically, if I were to let me erase this. Okay. So our polynomial will look like this. So I'm going to start from the left-hand side. So when it tends towards negative infinity, it's heading towards positive infinity, right? So when it's heading towards 0, that means that it's heading towards the 0, right? And when it hits the 0, it goes to the negative side, and it has to go towards the other 0, right? And we keep doing this with all the zeros, right? So when it comes to a 0, it will have a local minimum, come towards the other 0, have a local maximum, come towards 0, have a local minimum, come towards the 0, have a local maximum, and come towards the last 0 and have a local maximum, and it goes back down towards negative infinity. So this is approximately what the function looks like. Okay. Now, if we want to accurately graph this function, we have to identify where the local maximums and local minimums are on this function. And to do that, we'll have to find the derivative, and by finding the derivative, we have to find the critical points, and by finding the critical points, then we have to identify where those critical points are maximum and minimums. Okay, and that's beyond the scope of this question for now, because it asks us to just graph it and to describe the end behavior of the polynomial function. Okay, so we have described what the polynomial, or the end behavior of the function is that the function as it tends towards infinity is going towards negative infinity, and that when it tends towards negative infinity, that the function goes towards positive infinity. So let me write that down and we can move on. Okay, so when x is heading towards infinity, r of x is heading towards negative infinity. And when x is heading towards negative infinity, r of x is heading towards positive infinity. Okay? So the solution is correct. Good work. Cool. All right. So, what is the recursive formula for a geometric sequence? Okay. So a geometric sequence is basically a sequence of numbers that follows a common pattern. Okay. In terms of a geometric sequence, each term in the sequence is multiplied by a common ratio. Okay. So we have our values of a sequence. So we have S1. Right? This is the first term, S2, S3, S4, Sn. Okay, so we can have n terms of our geometric sequence, right? And each term of these sequence is related to each other. Okay, so S1 is by itself just S1, but S2 can be said to be S1 times what we have as a common ratio. R. Okay? S3 can be S2 with a common ratio R. S4 is equal to the common S3 times the common ratio of R. Right? And if we keep going, then Sn can be related to Sn minus 1 times common ratio of R. Okay? So these are equal to each other. There's another way to describe the terms in a geometric sequence, and we relate it to the first term. Okay? So S1 stays the same again. S2 is S1 times R, right? But S3, which is equal to S2 times R, can also be written as S1 times R times R. Okay? S4, which equals S3 times R, can also be written as S1 times R times R times R. Okay? And if you keep going, Sn can be written as S1 times R to the power of n minus 1. Okay, so these are different ways of describing each terms of the sequence, right? We can each either describe them as independently from each other, or related to the previous term, or related to the first term, right? So this is what a geometric sequence is. Okay, and these are the general formulas, right? So when they're asking us for a recursive formula for a geometric sequence, a recursive formula is basically a formula which uses the previous term of the sequence to find the next term of the sequence. Okay, so that's what it means by recursive. Okay, so the recursive formula for a geometric sequence would then be given as an, or the nth term of the sequence, is equal to an minus 1, so the previous term of the sequence times r. That's what a recursive formula is for a geometric sequence, right? So finally, I just want to describe what the formula, or the general formula for this sequence is, okay? So the general formula for this sequence, I'm going to write it in green to differentiate from this, is, so the nth term is going to be a1 times r to n power of n minus 1. So this is the formula for this sequence, and this is the formula for the blue sequence. And this is our recursive formula. This is our general formula, okay? So the solution is correct. Good job. Cool. All right, let's move on to question number 9, and this relates back to question number 1. Okay, so question number 1, we were trying to find the solution to the system of linear equations. So previously I described that another way to write it is that we want to find a point of intersection between these two lines. Now there could be three different answers, or there are three different types of solutions. Okay, we can either have no solutions, one solution, or infinite solutions. Okay, now if we were to have three linear equations, then we would possibly have multiple other solutions. Okay, but in a case where there's only two linear equations, we can either have no solutions, one solution, or infinite solutions. And I'll get into the cases of why. Okay? So, if we had zero solutions, this means that the linear equations have no point of intersection, or POI. Okay? And this is mainly because they have the same slope and they're parallel to each other, or that's essentially why. They have the same slope, or they have the same positive slope or negative slope, and they never intersect each other. Okay, so that's why they have no point of intersection if they're parallel to each other. Okay, and if you want to visually represent it, it will look like something like this, where there's two lines and they're parallel to each other, so they never intersect. Okay, so they have the same slope, not the same y-interception. So, if there's one solution, that means the linear equations have one point of intersection. Okay? That means if I were to graph it out, that means that they're not parallel to each other, they don't have the same slope, so they look something like this. It could be a positive, negative slope, it could be positive, positive, doesn't really matter, but there's one point of intersection here. Okay? Now, if there are infinite solutions, linear equations have infinite point of intersections. Okay? Right? Oh, this was supposed to be in green. Whoops. Okay. So what does it look like graphically, right? So if the linear equations have infinite solutions, that means that they are the same line, basically. So there's only one line, and that means that they intersect infinitely because of the same line. Okay? So when you're looking at a system of linear equations, you need to keep this in mind, right? Because it's very easy for us to just dive right into using the techniques of substitution and elimination. But if you're able to understand the concepts behind this, then you're able to just analyze our system of equations and come to a conclusion. Does my system have one solution, zero solutions, or infinite solutions? Okay? So let's look at our example here. So we have y equals 5 over 2 times x plus 2. And we also have 2y equals 5 over 2x plus 4. Okay? So you can take your pick on which one to use. I'm going to use substitution. Okay? So that means that I'm going to isolate for y for our second equation. So that means I'm going to divide both sides by 2. Also, this shouldn't be divided by 2. It should be 5x. Okay, so for 2, we're going to isolate for y, and we're going to divide both sides by 2. So we get 5 over 2x plus 2. So now, here is our system of linear equations. Let me just identify that these are two different equations here. Okay. Now, before we jump into subbing in or using the technique of substitution, we have to analyze this, right? So we know that in a system of linear equations, there are either one solution, zero solutions, or infinite solutions. And we know what that graphically looks like. Now, we see here that our system of linear equations here, they have the same slope, right? So that means that they're parallel to each other, right? And if you look further, they have the same intercept. They're basically the same linear equation, right? So because of that, we're able to not even calculate what the substitution would be, and we are able to just simply say that this system has infinite solutions. Okay. Now, if you were to sub it into here, you would get that you would have basically 0 equals 0. And when you have a 0 equals 0, that means that you have infinite solutions. Okay? So other than that, this solution is correct because the junior tutor said that there are infinitely many solutions. Good work. Okay, finally, let's talk about question number 10. So question number 10 asks us to solve the equation log base 4 of a plus log base 4 of 9 equals log base 4 of 27. And they basically want us to find the value of a, which makes this equation true. Okay, so we're going to use some properties of logarithms to help us simplify this equation. So the first one is the product rule, which states that the log of base b of a plus the log base b of c is also equal to the log of base b of a times c. Okay, so this is the product rule. We're also going to use the quotient rule, which states that the log base b of a minus the log base b of c is also equal to the log base b of a divided by c. And the final property is that we want to know that the log base of b of a, which equals x, can also be written as b to the power of x equals a. Okay? So we're going to use these three properties to help us solve for a. Okay? So the first thing that we're going to do in our expression here is we're going to isolate, or we're going to move all our terms to the left-hand side. Okay? That'll make it easy for us to solve for a. Okay, so if we were to do that, we would get log base of 4 of a plus log base of 4 of 9 minus log base of 4 of 27. Okay, so at this point, you can calculate the log base of 4 of 9 and 27, and then isolate for a, but that's kind of trivial. We're going to use our properties of logarithms to simplify our expression here. Okay, so first of all, we're going to use the product rule, which states that the log base of 4 of a plus log base of 4 of 9 is also a times 9, or 9 times a, minus log base of 4 27 equals 0. And similarly, we're going to use the quotient rule to say that the log base of 4 of 9a minus log base of 4 of 27 is also equal to log base of 4 of 9a divided by 27 equals 0. Finally, we want to convert our logarithmic form to exponential form. So we're going to raise both sides to the power of 4. Okay, so we're going to apply 4 here and 4 here. So what does that look like? We're going to do 4 to the power of log base 4 of 9a divided by 27 equals 4 to the power of 0. So basically, I converted this to exponential form by basically putting the base of 4 on both sides. All right. So by doing this, we now are able to isolate, get rid of the log base of 4, and we have 9a divided by 27 equals 4 to the power of 0, which is equal to 1. Okay. Now we can isolate for a, which is going to be 9a equals 27, and a is equal to 3 if we divide both sides by 9. Okay. So we got here from this step to, from this step to this step by using our logarithmic to exponential form, which states that the log base of 4 of 9a divided by 27 equals 0 is also the same thing as writing 4 to the power of 0 equals 9a divided by 27. Okay, so we got from this step to this step by doing that. Okay, so we have found the value of a, which makes our original expression true, so this solution is correct. Okay. So that wraps up my lesson today. I covered 10 questions related to functions and also a little bit of calculus. So if you have any other issues or problems with your homework pertaining to math or chemistry, please submit them to OneClass and we'll get that done as soon as possible. But other than that, I wish you guys